In this chapter, we're going to be looking at conjugated pi systems. Not only are we going to be looking at reactions, but we're going to look at the special spectroscopy that conjugated pi systems have. A pi system is conjugated when the double bonds are all in a row with no carbons that are fully saturated between the double bonds. So on the left, you have conjugated conjugated pi system, and on the right, you can see the double bonds are between the left and the right double bonds have a methylene group between, and so they're isolated. And the two that are end to end, those are called cumulated, and those are not conjugated either because the pi systems are at 90-degree angles of each other. Conjugated systems have special stability. They have lower energy than the sum of isolated double bonds. Not as low as an aromatic system, but still lower. When we look at a conjugated pi system, as in benzene, all the p orbitals, any aromatic system, all the p orbitals are in one pi system. And when it's conjugated like this, even though it doesn't come around and connect on itself in a ring, all the p orbitals are in one pi system. And the way that we describe this is with molecular orbital theory. So here is the simplest conjugated pi system we can have, two double bonds adjacent to each other. 1,3-butadiene has 4 p orbitals from each of the 4 carbons. Each carbon is providing 1 p to the pi system. Each carbon is sp3 and provides that 1 p with 1 electron in it. So this is what, if you line it all up, you would see these p orbitals all lined up together, and because they can overlap side to side all the way through, they act as one orbital system. It's not one orbital, but one orbital system. So there are 4 p orbitals and 4 electrons, 1 from each carbon. These all make these molecular orbitals. 4 p orbitals are going to give 4 pi orbitals. The lowest energy have all the p orbitals in sync. Next, you have one node right in the center, splitting it in half. The next up highest, you have 2 nodes. The next up higher, you have 3 nodes. Every node you put in raises the energy. The non-bonding energy would be at the dotted line that separates the 2 below and the 2 above. That would be the non-bonding energy. The 2 lower energy orbitals are below that non-bonding energy, so they are bonding. The 2 orbital systems that are above the anti-bonding, the 2 orbitals basically, above the non-bonding energy are anti-bonding orbitals. The 4 electrons are going to go to the lowest energy place, and so where do they go? They go to the bonding orbitals below the non-bonding energy. And that gives us those 2 orbitals occupied and the 2 anti-bonding orbitals unoccupied, which is pretty stable. We call the lowest unoccupied molecular orbital the LUMO, and we call the highest occupied molecular orbital the HOMO. And it's important for us to understand because when you have pi systems react, they're going to either be accepting electrons or giving up electrons. And if they're accepting electrons, they have to accept them into their LUMO. And if they're donating electrons, they have to give them up from the HOMO. And so if we understand this, this helps us understand why reactions go the way they do. Now, if you look at butadiene, we write it with 2 double bonds. But if you look at that lowest bonding orbital, you can see there's bonding between the 2 and the 3 carbons because they're in sync there. If you go to the next orbital up, there is a node, and so there's no bonding from that orbital between C2 and C3. But because there's so much bonding spread out over all 4 atoms, in the bottom one, what you find is the double bond strength in C1 to C2 and the double bond strength between C3 and C4 is reduced, and there's double bond character between C2 and C3. This is proof, or not proof, this supports the molecular orbital theory idea of pi systems and forming this pi orbital system that we're showing here, because you do have some double bond character between C2 and C3. So the double bonds are not acting in isolation like we draw them. They're acting as one entire pi system. So homos and lumos in a pi system are very important for determining how the reaction progresses. If you have a nucleophile or a free radical, it has a homo that it's using to interact with the lumo of its substrate. If you have an electrophile, its lumo is interacting with the homo of the substrate. And so we will see this later on when we look at Diels-Alder reactions, and we will see this later on sometimes in just discussing how simple reactions occur. For every pi system, what you have is the number of carbons that are in that conjugated pi system is the number of pi orbitals that you have in the molecular orbital system. The number of electrons is 1 from every neutral carbon. If you have a negative charge, there's going to be an additional electron. If you have a positive charge, of course, you'll have 1 less electron. So now that we've gone over conjugated orbitals, homos and lumos, now let's go and do some problems on this so that we can understand this a little bit better. If you try problems, you'll understand better. So, how many conjugated pi orbitals are made when you have a conjugated triene? 3 enes. Well, if we look at a triene, there are 6 carbons in the pi system. Each one of them is going to provide 6 orbitals. 6 orbitals provide 6 p orbitals will create 6 pi orbitals. So you have 6 pi molecular orbitals. How many of them are bonding and how many are anti-bonding? Well, if you remember our butadiene molecular orbital, you saw half were bonding and half were anti-bonding. The same thing happens with these 6 orbitals. What you have are 3 are bonding and 3 are anti-bonding. What happens to the number of nodes in the orbitals as you go up in energy? The number of nodes increase. The lowest energy orbital has no nodes, and the highest energy orbital has a node between each p orbital. Which has more nodes, a homo or a lumo? Well, since a lumo is higher in energy than a homo, the lumo will have more nodes. How many p electrons are in a conjugated triene pi system? There must be 6, because each carbon provides 1 p that has 1 electron, since it's a neutral system. Now, if you have charge, it would change. What orbitals would these 6 electrons be in? They would be in the 3 bonding orbitals. The anti-bonding orbitals would be unoccupied, so you would have 2 in each of the 3 bonding orbitals. Which would accept electrons and which would give electrons? A lumo or a homo for each? Well, Since a LUMO is unoccupied, it must be what accepts. And since a HOMO is occupied, it must be which gives.